Hi everyone, I'm Wang from Tsinghua University. Today, I will introduce our work, Pacman, an efficient compaction approach for log-structure key-value store on persistent memory. This is a joint work between Tsinghua University and Huawei Technologies. The new memory technology, persistent memory, brings both opportunities and challenges to storage systems. PM provides many attractive benefits, such as data persistence and byte addressability. However, PM also has some idiosyncrasies that programmers should be aware of. For example, compared with DRAM, PM has high access latency, about 300 nanoseconds. PM also has much slower write bandwidth. The write bandwidth per DIMM is about 2.2 GB per second, which is about 1/6 of that of DRAM. The access granularity of PM, also called XP line, is 256 bytes, which is 4 times the size of cache line. The mismatch of granularities can generate write amplification. Recent PM-based key-value stores adopt the log structure approach to reap PM's full potential. The figure shows the typical overview of log structure KV store. They append KV objects sequentially in a storage log. For in-memory storage, each service thread usually maintains a per-thread log for better thread scalability. Each thread can only write to their local log, but can read all other logs. Objects' location within the log are tracked by an index data structure, such as a hash table or a B+tree. In this talk, the location information in the index is also called reference. Log-structured approach has advantages like fast allocation and high capacity utilization. Besides, the sequential write and the out-of-place update pattern can also achieve small write amplification and easy failure recovery on PM. In the past few years, researchers have designed many in-memory log structure KV stores. However, garbage collection or compaction is the main overhead of log structure approaches, especially at high capacity utilizations. For example, from the evaluation results in RAM-Cloud's and Nible's paper, at high memory utilizations, RAM-Cloud's throughput drops by 20 to 50%, and Nible's throughput drops by up to 75%. Though over-provisioning can mitigate GC overhead, it is not cost-efficient. Some companies have expressed that they have attached importance to capacity utilization. For example, Google wants to keep disks full to minimize storage TCO. Facebook shows that space utilization is far more important than write amplification, and their optimization target shifts from optimizing performance to optimizing efficiency. So how do PM-based log structure KV stores behave at high capacity utilizations? We found that PM's idiosyncrasies exacerbate the bottleneck of compaction. We conduct experiments on state-of-the-art PM-based log structure KV stores, Blackstore and Viper, under a typical YCSBA-like workload. The figures show their throughput at different capacity utilizations. We found that at high capacity utilizations, the performance of both Blackstore and Viper drops obviously. Even if we double the cleaner threads from 4 to 8, the help is very limited. We found that existing compaction approaches are unaware of PM's characteristics. Therefore, can we improve the compaction efficiency according to PM's characteristics, and thus improve log structure KV stores performance at high capacity utilizations? Next, I will introduce our approach, Pacman, and PM-aware compaction approach for log structure key-value stores. Before diving into the design details, let's analyze the exact overheads of compaction first. During compaction, the cleaner will scan all objects in the old segment. First, the cleaner will check whether an object is still valid which means it has not been updated or deleted. Then, if the object is still valid, the cleaner will copy the object to a fresh segment and persist it. After that, the cleaner will update this object's reference. Therefore, others can find the object in its new place. When updating object's reference, or when checking the object, cleaners should traverse the index to find the reference. However, the traversal has several random access and is slow. The high access latency of PM makes it worse. According to our evaluation, the index traversal contributes the most overhead in compaction. The second problem is extra persistence work. To guarantee the copied object is persisted in PM, one flush instruction and one fence instruction are needed between step 2 and step 3 for each valid object. Besides, if the index is also on PM, one serial flush is also executed on the reference before handling next object. However, since the flush and the fence instructions are expensive, this extra persistent work slows down the compaction in PM-based systems. The third problem is a large amount of data copying on PM. When capacity utilization is high, there are less garbage in the segment, so cleaners need to copy more data to reclaim space. However, this data copying in compaction will consume PM's limited write bandwidth and contend with foreground service threads. The fourth problem is excessive small random access on PM. Besides in background compaction, in the foreground, service threads also generate many small random access on PM for garbage collection. For example, after appending a new KV object, the service thread will update the object's reference. If the object has old version, to facilitate garbage collection, the service thread will mark the old object's deleted flag in PM and read its size from PM to increase old segment's garbage bytes, which is used to select segment candidate in compaction. However, these small random reads have high access latency, and these small random writes result in write amplification and waste PM's limited bandwidth. To solve these problems, Pacman introduced several techniques. The first design is to use shortcut to traverse the index in compaction. Shortcuts point at the reference in the index directly. Here, we take a tree-based index as example. A shortcut contains two parts. The node ADDR points at the leaf node, and the KV post indicate the exact index entry in the entry array. For example, if a cleaner wants to find the KV2, a traditional approach should search from the root node and traverse the long path layer by layer to the leaf node. Now, with shortcut, the cleaner can skip the high latency root to leaf path and get to the destination directly. Shortcuts are recorded by foreground threads in parsing when writing the KV objects and stored with the corresponding objects in PM log. However, as the index keeps inserting and deleting KV pairs, its structure may change and shortcuts may become invalid. There are three situations of shortcut invalidation. First, the KV post is invalid, which is caused by shift operations. For example, the KV post now is pointing at the second place KV1, but the real reference of this shortcut is KV2. In this situation, the cleaner will first check the header of the leaf node to make sure the reference is still in this leaf node. Then, it researches the leaf node to find the real reference. The second situation is that the reference has been moved to another node, and the node ADDR points at a wrong node. In this case, the cleaner will first try to search the sibling node. If it fails, the cleaner falls back to the normal search operation, research the reference from the root node. The third situation is that the original node pointed by the node ADDR has been deleted. In this case, the improper access is dangerous. To prevent this situation, Pacman will not delete the index node physically, but logically, such as marking the node as deleted in its header. Then, the space of the deleted node is reserved for future allocation. The cleaner will fall back to the normal search operation to find the reference. Since delete operations are not very frequent in real-world production workloads, Pacman will not reserve too many nodes. The second design of Pacman is redesigning the compaction pipeline. As in existing compaction approach, the compaction is conducted in a per-object manner. Each object is handled entirely one by one. In this manner, one flush and one fence are needed for every valid object, and flush on the reference are conducted serially. To reduce the extra persistence work, we redesign the compaction pipeline to batch manner. In the batch manner, the cleaner first copies all valid objects in the old segment to a volatile buffer. Then, it uses non-temporal stores to copy these objects to the fresh segment. Non-temporal stores move data directly to PM and bypass the CPU cache. Non-temporal store has higher bandwidth than normal store operation for bulk of data. Third, the cleaner updates these objects' reference with shortcuts and persists them in batch. In this manner, only one fence is needed between the second step and the third step for the whole segment. As some flush instructions like CLWB can be executed concurrently, when persisting reference, the cleaner can launch concurrent flush instructions on the batched update reference. Furthermore, the cleaner prefetch reference via shortcuts to cover the access latency. To reduce the amount of data copying, the third design is separating hot and cold data. It's well known that separating hot and cold data can reduce the overhead of garbage collection for log-structured storage systems. However, for an in-memory system, the approach to identify hot and cold data should be lightweight enough. Pacman used an in-DRAM immutable hot set to identify hot and cold data. The immutable hot set contains hotkeys hash values. We use an immutable data structure because a dynamic data structure has high overhead of contention. Now, each service thread maintains two thread local segments, one for hot objects and the other for cold objects. In this way, since hot objects are updated more frequently, hot segments will gather more garbage. Thus, Compaction will prefer hot segments to reclaim space, which has less overhead. In real-world workloads, the hotspots may change and the immutable hot set will become inaccurate. To handle this situation, each thread will count the hot object's proportion and record key hash of written objects by sampling in their local buffer. If the reported hot proportion is low, which means the current hot set is not accurate anymore, a background thread will collect records from each thread's record buffer. Then, it generates a new hot set according to these records and replace the current hot set using epoch-based technique. If the background thread finds the records are distributed uniformly, it will set the hot set to empty. The fourth design of Pacman is to reduce excessive PM access. Recall that in the foreground, for each updated object or deleted object, the service thread will read its size from PM to increase old segments garbage bytes, and write old objects deleted flag in PM. These small random access on PM have high overheads. To reduce the PM read of size, Pacman embeds the size information in the upper 16 bits of reference value. Therefore, the size can be acquired from the index when updating reference. To reduce the PM write of deleted flag, Pacman adopts a deleted flag bitmap on DRAM for each segment. Pacman locates the corresponding bit of a variable size object with its offset directly. We denote the minimum size of an object as min size. The bitmap reserves 1 bit per min size. The position of the deleted flag is calculated by dividing the object's offset by min size. In the most extreme case, the min size is 24 bytes, which includes 8 bytes of key, 8 bytes of value, and 8 bytes of metadata header. In this case, the bitmap only consumes 0.5% of space of pmlog. There are also some other design details, such as how to optimize space overhead of shortcut and the recovery of Pacman. If you are interested, please check out our paper. Next, I will report some experimental results. Our experiments are conducted on a server within one NUMA socket to avoid NUMA effect. Each CPU socket is equipped with 3 Optane DIMMs and 96 GB DRAM. We apply Pacman on 2 state-of-the-art PM-based log structure KV stores, FlatStore and Viper. We apply 4 versions of FlatStore to evaluate different index types, including hash table-based and tree-based, volatile and persistent index. Benchmark workloads include YCSB with different settings, and their production workload Facebook etc. pool. These figures show the overall performance under a typical YCSBA workload, which is the same evaluation we showed in the motivation. We evaluate these systems with small value size, which are common in production KV workloads. In these figures, x-axis is the capacity utilization, and the y-axis is the throughput. From the figures, you can see that Pacman obviously curtails the performance decline at high capacity utilizations and achieves 1.5 to 3.5 times speed up. Pacman also enhances the performance at low capacity utilizations, where compaction are not very urgent. This is because Pacman reduced the small random access and saved PM's limit bandwidth. Then, we vary the workload settings, including uniform distribution, different thread counts, different value size, different write ratios, and different numbers of objects. These results show that Pacman is effective in write-intensive workloads with various settings. Facebook etc. pool workload has a mixture of small and large KV pairs, which represents real-world production workloads. There are 40% of KV items with size smaller than 13 bytes, and 55% of KV items with size smaller than 300 bytes. The get-to-put ratio is 50 to 50. We compare FlatStore with Pacman against other 3 systems, Pman RocksDB, a Pman version of RocksDB, and Pman KV from Intel Pman DK group, and ChameleonDB, another log structure KV store with a well-designed hybrid index. We set all systems using the same amount of CPU resource. Since Pman KV doesn't need background threads, it uses 28 threads, and others use 24 foreground service threads and 4 background threads for compaction. The capacity utilization of ChameleonDB and FlatStore is set to 80%. Figure A shows the throughput, and the other 4 figures show the median and tail latency. From these figures, you can see log structure KV stores have higher throughput and lower latencies, which proves log structure approach suits PM well. Our Pacman further enhanced log structure KV stores. Finally, I will present a brief conclusion. We found that current compaction approach are unaware and not well designed according to PM's characteristics. However, PM's characteristics exacerbate the bottleneck of compaction in log structure KV stores. We propose Pacman, an efficient PM-aware compaction approach for log structured KV stores on PM. We apply and enhance